Okay, so we're going to start 6-1 today, which is Introduction to Limits. We're going to spend the next 2 weeks, or the rest of this course, working on limits, which is an introduction to some calculus concepts. For those of you who are going on to college and you're going to take college algebra, or maybe possibly pre-calculus or calculus in college, you're going to need to know these concepts of limits. And for those of you who are doing anything else or not going to be looking into math anymore, well, you'll have learned something interesting, I guess, the last few weeks. So example 1, describe the end behavior of the following rational functions as infinity, at infinity and negative infinity using limits. So a limit is basically about asking what the value is depending on how you're approaching it. So if we're looking at a function, which is a graph, and we're saying, depending on how we're approaching it, what is the limit or the value at that point? So that's what we're looking for to figure out. So the first one is a rational function, and we look at the degree of this function. These are both first degree functions because the exponent is 1 on the top and bottom. And when the degree is the same, that means the function is going to have a horizontal asymptote. We talked about this in our first unit, way back, unit 1 in January. So we had a rational function in which the degree is the same for top and bottom. We have a horizontal asymptote, and to find the value, we take the coefficients in front, 4 over 1, y equals 4. And if we draw a quick little sketch, what does that mean? If we go up 4, we have a horizontal asymptote at that value. We also have a vertical asymptote, which is defined by the denominator. When we find the vertical asymptote, we set the denominator equal to 0, and that tells us we have a vertical asymptote at x equals 1. So this is what our graph looks like, and we want to know the end behaviors as it says to do as we approach infinity and negative infinity. So the limit as x approaches negative infinity, f of x is going to equal, and so as we go towards negative infinity, we come down towards negative infinity. What is happening to our graph? It's getting closer and closer to the horizontal asymptote of 4. Okay, and then if we say the limit as as x approaches positive infinity, the graph is coming up and going along and getting closer and closer to 4 coming from the bottom. So no matter what direction we're going in, the graph is going to approach 4. So the limit from the negative infinity and positive infinity is 4. So now we'll look at some more graphs just to think about what a limit is and help define what a limit is, and then we'll look at some more examples. So the second one here, we've got a graph, and there should really be arrows at the end of this. So we have a graph, it's a line, okay, and it's going along here, but it has a hole. So if we remember, this point is called a hole, and at that point, there's no value or it's undefined. So this occurs when we have a value in the denominator. So if we had a linear graph, but x is in the denominator, cannot be, in this case, x can't be 1 because it would make it undefined. Okay, so when we're looking at the limit of f of x, and we're going to say as x approaches that value 1. So as x approaches 1. So as we go from here towards x is 1, or from here towards x is 1, we're approaching that hole. So what is the value that is approaching is what the limit means. So what value is the graph approaching? Well, the graph is approaching the value 2 from either way. Even though it will not actually equal 2, when we say the limit, even though we write the equal notation, what it is saying what is the graph approaching. So when you're doing limits, what you're doing is you're predicting the y value as the graph approaches a point for x. So we define the x value we're approaching. So as we approach x is 1 from either direction. Sometimes they'll tell you from a positive or a negative. This, if it doesn't say the direction, you're talking about from both. So from either direction, as we approach x is 1, which is this line here, What is the graph approaching? It's approaching the value 2. Approaching. It doesn't mean it's going to actually get there. It's approaching. So limit notation is only what it's approaching. Okay, so let's look at another example. So here's another graph at the top. Same idea. We've got arrows at both ends. In this case, it's coming up and along. These lines, sorry, those are drawn in. Kind of talking about how the different values along here are all going to be approaching and coming closer. But really, it's just a line, open hole, and there's a point up here. So the graph has jumped. Okay, it has a jump. We call this point discontinuity when we're talking about this, it jumps. But if we think about our limit notation and what the limit notation means, and we say, well, what is the limit as x approaches 1 from the negative side? And then let's do the same thing. What's the limit as f approaches 1 from the positive side? So if we go from the negative side, we come up and we go towards, so as we approach 1 from the negative side, or what happens? The graph is still approaching 2. As we approach it from the positive side, the graph is still approaching 2. Even though at the value we know it's not 2, it's somewhere around 4, what is it approaching? It's approaching 2. The line is going towards 2. Okay? And because these both have the same result, we can write the limit of x approaches 1 from either direction. Remember, if there's no direction there, f of x is going to equal 2. So now let's look at the next one. We've got our arrows at both ends. This one is a line and that point is included. So this we can again from either direction, the limit as x approaches 1, f of x is going to equal, and in this case it really does equal 2. Okay? So whether the hole is open or closed, whether it jumps or not, it's going to be approaching that value. So those are all just different instances of the same exact graph with different behaviors. Okay? So now let's look at a different graph. So here we've got the graph. We've got a line, a horizontal line that includes a point 2 going left, and a horizontal line that does not include the point 2 going right. So for this, we have to think about approaching from the left and the right. As x approaches, the value here is 2, so we're going to say as x approaches 2 negative, okay, that means from the left, f of x is going to be approaching 1. So as we come from the left towards 2, what is the graph heading towards? What is the value there? It's 1, 2. However, if we do x approaching 2 from the right, f of x equals, if we start on the right and we grab our graph and we start approaching 2, what is the value here? That's not 2, that is 5. So do you see how the difference, if we're approaching and the graph is approaching from the left and it's getting towards one value, but from the right it's going towards another, then we have two separate statements. So therefore, if we try to write the limit of f of x as x approaches 2, not from any particular direction, so we're not going from left or right, we're just approaching 2, the answer is going to be not defined, because it has different values depending on the direction, so we can't summarize and say what it does. Up on this problem, it was the same, so we say the general limit approaching 1 from any direction is 2. Here, because it changes depending on the direction you're coming from, it's not defined when we try to summarize in any direction. We'll see more problems and more examples of graphing on tomorrow's lesson. So now we're going back into no graphs, just talking about the concepts of limits. Translate the following statement, excuse me, into a limit notation. Excuse me again. So the limit of y equals 1 over x squared as x approaches infinity is 0. So to translate this into limit notation, we're going to say the limit of 1 over x squared, so we write the equation, as x approaches infinity is 0. So we're just writing, this is the words, this is how we read it, this is how we write it. So this is just asking us to write it into this notation. So the words into the notation. The next one, translate the following statement into words. We've got some more interesting looking problem here. We have sum notation we've done last unit. Okay, so to think about this, we've got limit. So the limit of the sum of, because this means sum, remember? And then we got to figure out the values. So if we look at this, it says starting with I is 1. So if I equals 1, we plug in 1. We have 1/2 to the first, which is 1/2. I is 2, because it says I is 1, and it says go on for any number of terms. So we're going to have 1/2 to the second, which is 1/4. If I is 3, we have 1/2 to the third, which is 1/8. So the sum of 1/2 plus 1/4 plus 1/8. And because it says all the way to n, which is any number of terms, we could say plus dot, dot, dot. This is going to continue forever. Okay, so the limit of the sum of 1/2 plus 1/4 plus 1/8 plus continuing on as the number approaches infinity is, and now we got to figure out the value. Well, it tells us right here is going to equal 1. So to read this notation and write it out, the limit of the sum of 1/2 plus 1/4 plus 1/8, continuing that pattern for infinity, would be 1. That is what that's telling us. So then the next problem says, how would we write the notation? So now we've kind of have this, and we need to write to look like this. So we're going to put the limit as n approaches infinity. All right, and then we're going to make our sum symbol. N goes on the top, I equals 1 on the bottom. And then we've got 1/3 as our starting value. And it goes 1/9, so we're raising it to the I power. So the first to the second to the third and so forth equals, and what does it equal? 1/2. So we wrote this notation into this notation. You're going to have some examples on your notes doing the same idea. Make sure you look for the pattern and figure out what's going on. I is the exponent, so figure out what exponent would go on the pattern. You've got your starting value, and then you can go from there. So you'll see some examples on your notes. Come to the class at noon if you need some help.